Okay, welcome to everybody else who joined from externally. We're going to wait a couple minutes, maybe 3 to 4 minutes, and then get started with the tech talk.
Are we live streaming this to our Facebook group too?
No, I didn't realize that you can do that. I probably should be doing that though.
Yeah, I've never actually. I think we did it for like one info session a few years ago. But yeah,
Oh,
this is the first time that we've been doing public events in a while.
yeah. I will investigate live streaming because I think that's probably better than that might, I don't know,
Yeah,
because if people join a Google call, then they can ask questions as well, which was pretty big last time.
yeah, I don't know if they're able to do that over Facebook. Maybe they can definitely like chat questions. I don't know about. Yeah, you probably can't join voice. That just be typing. The other nice thing about the Facebook recording. I don't know how we're like broadcasting this afterwards, but like it automatically records the presentation and then like it's accessible on your page even after the live stream is done.
Oh, that's nice actually. My plan was just to record this and then upload it to our private Google Drive. But having it open would also be nice.
Yeah.
Okay, awesome. Why don't we get started then? So to the new students that have joined us, I'm Charles. I'm our team captain for Autonomous. So today we're going to be going through our second tech talk on our so the first one 2 weeks ago was on our sensor data. So that feeds perfectly into this second tech talk where we talk about how we use that perception data, that sensor data, to get an understanding of our environment. So we'll be talking through our perception stack, including object tracking, object detection, road line detection, and traffic light detection. With me, I have three members of our perception team: Anita, who leads the perception team, as well as Sinclair and Martin, who work very closely with the projects on there. So I will hand it off to Anita to give an overview of what we're going to be talking about and to set it off.
Thanks, Charles. So for this tech talk, we'll be talking about the perception tech pipeline and going into detail each of our algorithms. So that includes object detection, traffic light detection, two approaches that we've used for road line detection, and lastly, object tracking. And then at the end, we'll have some time for questions and answers. Next slide, please. And first, I'll talk about the competition constraints that we have. So for the auto drive challenge, we are restricted to not using GPUs. So that is a pretty big constraint, considering that a lot of companies use a lot of neural networks in their detections. So that is a big constraint for our algorithms. And in terms of driving in the map, we need to hit a required speed, and the maximum speed that we use is 25 miles per hour, and that is a constraint on our detection speed that we need to reach. Also, MCity has very unique objects that we don't see in other parts of the, I guess, data sets that we see in public. So that provides a challenge since we don't have all the objects that we want to detect in open source data sets. Simulation is a new constraint because of the pandemic, and we can't go testing outdoors very often. And lastly, as I talked about before, is there is very limited number of public data sets that are good and we can use. And yeah, next slide, please. So first I'll talk about our entire perception pipeline. Here you can see the picture. So from the inputs, we have one LiDAR, and 3 cameras. So the LiDAR is used for object detection, with the right and left camera is used in traffic sign and object detection, and also traffic light detection. And the center camera is only used for road line detection with a fisheye lens, so you can see wider parts of the road. And basically, our outputs to path planning includes tracked signs and obstacles, all in 3D, and traffic lights and road lines, which will also be in 3D and classified. Next slide. So now I'll go deeper into detail for object detection. So I guess assuming very minimal knowledge about convolutions, so we use convolutional networks a lot in our perception algorithms. And so first of all, what is a convolution? So the convolution is the idea of using a kernel. So in the GIF, you can see a 3x3 kernel that is being applied to the image. And basically the operation is that you multiply the kernel with values in the image and sum that together to get one value in the output, so which is the green square on top. And so basically that operation allows us to extract starting at like lower level features, which is, for example, edges, as you can see in the other image. And then as you get deeper into the network, we get more and more complex features that it can recognize, such as curves and, for object classification, for example, eyeballs of animals, and etc. So next slide, please. So for object detection in the camera frame, we use the YOLO V3 model. So that is a basically, I guess, kind of older now, but it was the state-of-the-art object detection neural network for a long time. And basically, it does predictions at 3 different scales. And the idea is that in the image, it splits off the image into grids. And for each grid, it predicts bounding boxes. And by doing that in 3 different scales, it allows the model to predict large objects, medium-sized objects, and also work well for small objects. Yeah, next slide, please. So for traffic sign detection, we don't, the signs that we want to classify don't exist in public data sets. So the choice that we chose is to go with synthetic data. So what we did here is we cropped traffic signs and paste them into random locations of the image and with different sizes, and also applied data augmentation, such as blurring dropout in brightness, as you can see in some of the images there. So the background images we are getting from a public driving data set so that it is relevant, and it produced pretty good results for the model that we're using. Next slide.
What? Okay, that's really weird.
But, okay. So now that we have the 2D bounding boxes, we want to get the 3D location of each object. So that we use Frustums. So the idea of Frustums is that the in 3D space, when you look at it from the camera's perspective, you get basically a 3D cone-like kind of shape that projects on to that section of the image plane. And what we have is that we generate these frustum shapes in the LiDAR point cloud and perform Euclidean clustering within each frustum. And we have a algorithm that determines the best 3D bounding box within each frustum, which is based on the IOU, which is intersection over union, with the 2D bounding box itself, and also based on the number of LiDAR points that exist in each 3D bounding box. Next slide. And here we have a demo of our detection algorithm. So this is in-car visualization showing the detection algorithm running with pedestrians and also a traffic sign. And yeah. So yeah, next Charles will talk about object tracking.
Awesome. Yeah, sorry about that bug earlier. Pressed the wrong button. But yeah, so now that we have these 3D bounding boxes for our objects, we need to track them between time. So the motivation here is that when we have a bunch of detections across multiple frames, we need to know which objects correspond to the same obstacle as it evolves through time. So what might happen is that these boxes might move around, they might get occluded by other objects, and they might even change shape a little bit depending on our detection algorithm. So in the end, we want to estimate the position at any time, the velocity, the dimensions, and also we want to assign an ID number to every individual object. So the object tracker that we use is a modified version of a very popular public repository. And this is called AV3D Mote, which is a baseline for 3D multi-object tracking. This is a pretty large space in developing object trackers. And this algorithm has been shown to be a very good baseline, a very stable performer in lots of different data sets. As a bit more context of why this is important, the tracked objects are mostly important for the path planning and prediction layers. So when you know that an object and how it's moving throughout time, you know how to predict what it's going to do. And that way you can make safe maneuvers by estimating what a car might do. For example, turning right or going straight through the intersection. The object tracking problem can be broken down into two main problems. First, I'm going to introduce some background terminology. So we call any object, like a singular object, say like one person whose name is John, the John person, as he evolves throughout time, we will call his bounding boxes a track. So the track will contain all of the state information we have about the obstacle, including his bounding box, velocity, history, and predicted future positions. So with those tracks, whenever we get a new detection, we essentially need to apply two stages. The first is a data association problem, where we need to associate the new detections to our existing tracks. Once we've done that, The second problem is a prediction problem. We need to take our track for the object and its current position, and we need to predict where it will be in the next frame. Once we run that prediction, we can once again apply association again with our new detections. This gives us a stable track throughout time. So as I was saying, right, we have our detections, we associate them, we create new tracks. So let's say there's a new object that comes up, we need to make new ones. We then need to predict the new position of every track, and then we delete the old unused track. So if, say, if an object has exited our field of view. So I'm going to focus on the two parts that I mentioned earlier. So for associations, we need two main things here. There is a metric and a matching algorithm. So the metric determines how similar a new object is to an existing object. And we can use two metrics here. There's the IOU, which is the intersection over union, calculated by the area of the overlap of the two bounding boxes divided by the area of their union. And this gives sort of a standard metric on how much two things overlap. There's also a statistical method called the Mahalanobis distance metric, which determines how similar a data point is to a set of existing data. So now that we have calculated the similarity metrics for all of our objects, we can create a one-to-one Hungarian matching. Hungarian matching is named after someone. I think he was from Hungary, maybe. But it's just a fancy word for saying a one-to-one mapping that has a maximal score. So an example can be shown on the right. We want to create a matching of as many of the left objects to as many of the right objects as possible in a pairwise fashion, such that the score along each of these edges is maximized. In our case, our score is the similarity metrics that we talked about earlier. Awesome. So now we've created a matching. And we've associated our old detections with the new detections. Now we need to evolve our existing tracks and to predict where they'll be in the future. We do this using a linear Kalman filter. So what a Kalman filter is a statistical method of predicting a best estimate given some data. So the data it needs is that it needs the previous state of the object. It needs a new measurement. It needs some sort of a motion model, so an estimate of how an object will evolve over time, and a measurement model, so how our measurements correspond to our state. And what the Kalman filter does is it produces the best estimate of our current state given this previous information and current measurement. And the benefit here is that not only are we predicting some position, we can actually prove that the estimate from the Kalman filter will be the best estimate, minimizing error, given our data. So the math is here on the right, but I won't go on to this, because it's very complicated. But I'm sure you can look up some online tutorials if you're very interested. And it's some cool math right here. But as a bit of a high level, the Kalman filter is basically able to determine how much weight to give the measurements and our previous state based on the data, and assuming some noise, which is generally approximately Gaussian or normal noise. So in autonomous driving, once we specialize the Kalman filter for autonomous driving, we use a state vector, so representing all of our objects using the XYZ positions, the heading, the length, the width, and the height, and the velocity in the XYZ direction and the velocity in the angular direction. Our new measurements are the position, XYZ, orientation, and the length, width, and height in the bounding box. We can clearly see, it's pretty easy to associate our new measurements with our existing detections. It's just we have a subset of our state that we can measure at every step. For our motion model, we assume that all objects travel with constant velocity. So this means that at the next time step, we can estimate that our position will be our previous position plus the velocity at that time. And then we assume that our position and our velocities are constant with some noise, which is represented by Q here. So there's a problem here, right? So in the measurement model that I've just shown you, we assume that all objects travel in a straight line with constant velocity. But of course, that's not going to be true. Our motion model and our measurement model will diverge. In that our measurement will probably like have the car turning, but our motion model will predict that it goes in a straight line. So that's why the common filter is great. As I was saying before, it'll find out how much, it'll find out a best estimate based on the existing data that we have. So the final estimate will be a compromise of our motion model and our measurements. Of course, there are a lot of possible errors in this scenario. So here, I have a couple examples of some things that could go wrong. So first, if in the A here, if our hypotheses measured by the H and the observations in the O are too far away, it's possible that our common tracks or our predicted objects will diverge from where they actually are. And of course, there we'll call it a false positive. It's also possible that if different objects get too close together, as shown in the second picture, the ID that we give them will switch. So the blue circles will be called, the blue circles will be blue circles, and then suddenly they'll be labeled as red triangles because they've gotten too close together and the IDs have switched. That's obviously not great. Another possible is the third option here where the ID has just swapped. So originally this orange circle was called a blue, and then after a couple time steps, it's now red. And then the fourth possible problem is if we miss some detections from a perception algorithm, it might cause some errors in our estimated states. So here I have a demo of our object tracking working with some test data. But you can see that with our car, we're able to track and label this object that is traveling through the frame, as well as a bunch of other cars and pedestrians. And they're assigned consistent IDs, and we can predict their velocity as they travel throughout the frame. Awesome. So next, I will hand it off to Sinclair to talk about our traffic light detection algorithms.
Yeah.
Wait, sorry. Is Sinclair speaking? I can't hear him. Is this my fault?
He is speaking, yes.
Oh no.
I think, yeah, I can hear it. Good.
Yeah, sorry about this in the recording, but I can't hear what Sinclair is saying, so I assume that the recording can't either. I'll double check it later, but basically, if I can explain briefly what this means, it's we take bounding boxes from the YOLO v3 detection algorithm that Anita talked about earlier. We then convert it to hue, saturation, and value, so a different color space. HSV is better than RGB for determining colors, as the different colors are much more, like a lot further apart in the spectrum, have different values. So from that we can determine, where the red is, where the green is. We then look at the contours of the arrows. So for example, this arrow, it has a clear shape. So we can determine that this is a left arrow and that this is a red, solid red block. Then based on the arrow, we can determine what direction it's pointing. So the majority of the pixels are on the left. So that means that this is probably a left arrow. If the majority of the pixels are on the right, we would think that's a right arrow. We then take all of these states from these traffic lights. So this is a left and this is a red. And then we aggregate those into a single traffic light as shown here. We can have track those across time. Okay, for the recording again, this is really unfortunate, but the first pipeline that we use for red line detection is a semantic segmentation based model. So semantic segmentation is the process of taking each pixel and classifying the pixel. So we can say in the example in the middle here that certain pixels are red, so that means that they're corresponding to like a middle of a road, and certain pixels are blue, corresponding to say like a white lane or the edge of the road. And then everything black has been classified as not important. So first we do the semantic segmentation. We then convert the image to a bird's eye view, so as seen in the slide labeled B. We then take a histogram of values to see where the actual lanes are. So you can see there are peaks at the center of each of the lanes. We can then use a sliding window, so a series of boxes sliding across the lanes to determine and pick up the exact location of all the lanes. And then once we have those positions, we can fit a line to those positions to produce a detected road line. These lines are then translated into 3D space. So, the lines are in bird's eye view. And then we know the measurements of where our cameras are. So we can translate these into 3D space. There's an additional step there where we can classify what the lane type is.
Charles, can you hear me?
I can. Yes, I can hear you.
Oh, that works. Okay. So we don't need to put it in the chat anymore.
I guess it's just Sinclair.
Yeah, so next slide. Yeah, thank you. Okay, so as Sinclair said, our current approach was a little error prone because of all of the manual tweaking and those manual algorithms. So we started looking into more end-to-end approaches, since when you look at a lot of these lane detention benchmarks, which are basically open source data sets that everyone can submit algorithms to, all of the top approaches are basically just end-to-end approaches. So it's a neural network that takes in the image and it directly predicts the lane lines without any of the post-processing that was needed for our past technique. And so we decided on a paper called Ultra-Fast Structure-Aware Deep Lane Detection. And this paper was chosen because it's very accurate on one of the most popular open source lane detection data sets called CU Lane. And it's also designed to be extremely fast, which is needed for us since we're running everything on CPU. And so if you look on the right side, basically what this model is doing is taking in the image, and then for each, it basically splits up the image into a coarse grid. If you look basically in the middle, top middle, you can see that the image is split up into a grid. And contrary to semantic segmentation, where you're predicting a class at every pixel. What we're doing here is for each lane, we're predicting basically the column for each row. So we're going row by row and predicting in which column of this course grid that the lane should be in. And then there's also the option for no lane being in the row. And so this is a lot faster than semantic segmentation. And basically it allows you to predict all these lanes end to end. So if you look right below this course grid image, you can see the actual model. And it's not a very complex model when compared to like something like a YOLO or a lot of these object detection or semantic segmentation models, because it was designed to be fast. But it's basically just a backbone network of convolutions. So these are ResNet blocks. And then basically you have a fully connected network, which is just like a regular non-convolutional neural network, which processes the output, and then it gets reshaped into this course grid that I talked about earlier. And so this is very fast because this ResNet block is relatively small. We could make it bigger at a trade-off for speed to get more accuracy, but we're mostly focused on speed. And then you'll also notice there's this second branch that comes out of the backbone network called auxiliary segmentation. And this is basically just during training. We're also predicting a segmentation output for the lanes, and this helps the model generalize better. But this branch is removed during inference for a maximum speed. And so if you look on the left, the steps for the pipeline basically get shrunk down a lot. So what you're doing is you're first predicting the lane locations using the end-to-end model. And this model was designed to predict up to 4 lanes. This basically depends on the data set it was trained on. CU lane has a maximum of 4 lanes. And what happens is it'll end up predicting basically the 4 closest lanes to the middle of the image. And then basically you can take this output, fit a line to it, and then translate it into 3D space, similarly to what we would have done with the last approach. Next slide. So this is an example of the end-to-end model being applied to a fisheye image that we collected in Waterloo. So you can see it's right next to campus, like the north side of campus. And you can see it generalizes really well because it was trained on a very large data set. And every single point in the image is one of those row anchors that was predicted. And then I just fit just a simple spline through it to connect all the points together. Next slide. So that's lane detection. And basically we're moving towards using this end-to-end model because it generalizes a lot better and it's less error prone. But this end-to-end model does not do another task that's needed, which is lane classification. So we need to know whether the lane is yellow or white, and also need to know whether it's dashed or solid. And there's multiple ways we could do this. One option is just to use OpenCV classical computer vision, which involves like yellow versus white color thresholding, and then basically trying to get a contour of the lane itself and looking at the features to see, basically compare the area, and a more solid area you can assume to be more solid. And then if it has a smaller area, you can assume it's more dashed. So that would be one technique. But another technique which we'll be looking into is basically just to do the classification with deep learning as well. And basically this process would just be to add another classification branch, which can be just some fully connected layers to the already existing end-to-end model. And then you would have to adjust the loss function to account for this classification. And then you would need to collect the data set with lane class labels and just train the model and iterate on it. And so what's going on here is kind of a form of multitask learning, where you have shared layers at the start, and then these are splitting off into specific tasks, which ends up producing a really fast network that can do a lot of kind of related tasks. Like you wouldn't do, for the most part, a multitask learning network that would, say, predict objects, and then it would also classify lanes. You tend to want to keep the task kind of relevant. And this is pretty popular, and it's good for us because it ensures maximum speed. So next slide. And here I'm just kind of gonna give a bit of an idea of why end-to-end kind of performs better than our other approaches. And this is kind of due to the fact that deep learning, with how many parameters it has, it kind of tends to scale a lot better with data in terms of performance than other algorithms or even like classical OpenCV approaches. They tend to, as you collect more and more data, they're not really adjusting to account for this new data, not like deep learning would. And so this is kind of something that we've seen throughout the years with computer vision and even NLP, where a lot of these huge benchmark data sets are basically being overpowered by deep learning techniques just because of how much they scale and how much they can find complex functions to fit to the data. And so an example I put here is ImageNet, which is one of the largest, well, not the largest, but it's kind of like the huge image classification benchmark that has kind of made computer vision what it is today. And the actual loss, like the top percent loss, has gone down tremendously since deep learning has gone on the rise, and now it's way below human level performance. Next slide. And so this is not really related to the competition, but it's a bit of a tangent. You would naturally maybe lean towards the idea of end-to-end planning or control for self-driving cars. And not a lot, but some of these level 2 companies are starting to adapt this, such as Tesla and Comma AI. And basically they realized that basically getting large scales and large data sets and then training them with networks is a really good technique for getting a model that will generalize well and basically perform well. Next slide. Yeah, so I guess now we're open to questions for basically any part of the slides.
I have a question. Am I allowed to ask a question? So I was
For what
wondering,
part?
yeah, so for this road line detection,
Yeah.
so if I understand correctly, the benefit of dividing it into this coarse grid is for speed, right? But are there any
Yeah,
sacrifices that
basically.
you get for doing this coarse grid?
I mean, if the grid was finer, you could probably get better performance. Because the way the data set is labeled is the labelers at each, they have basically every 10 pixels going up through the image, they would label basically which column the label's in. And so you could get slightly better performance by using a finer grid, but you would be sacrificing speed at that point. So this is something you could play with. It's just something the authors decided to choose a specific grid just because they kind of played with it and decided on that specific grid.
So is it a custom data set with labels specifically for this model, for this grid?
No. So there's, as I know of, there's 2 data sets that use this kind of labeling format where they go up 10 pixels at a time and then label which column the lane's in.
Right.
And they're 2 simple and CU lane data sets.
Hmm.
And these were already pretty popular before this model came out, but this model was kind of designed specifically for that labeling format for the CU lane dataset.
Smart.
Yeah. Yeah. So that was just an image that I got that was collected in the car. So we have a bunch of they're called ROS bags. So we use ROS. You can collect data from all of the sensors using ROS. And I just got it from one of our data sets and applied the model on it. We haven't really tried to run it in the car itself because the rugged is down. But this is something we'll be trying to get once the rugged's back up. No problem.
So how fast does this model actually run?
Oh yeah, I didn't mention that. So the authors, well, the problem is we don't have a GPU, but the authors using a 1080 Ti were able to run the model at I think like 325 frames per second. So it's plenty fast. But yeah, we haven't really run it on CPU yet. But we're planning on testing it on the rugged. Like if this runs too slow, then honestly there isn't really much you can do since it's such a small model.
Yeah, 325 feels pretty fast.
Yeah, it's really fast. It's a very small model. Yeah, it's I could reduce it and then retrain. There's other things I could do to get better speed boosts, such as like reducing the input image size, or even using like a smaller backbone. Like the output grid size isn't what's slowing down the model that much. There really isn't much that's slowing down the model because it's just insanely small. But yeah.
I think there's I think there's like there are like a machine learning libraries to use with Spark, which is like a distributed language, right? So technically, if you're worried about speed and like speed because of like the data size, I mean, theoretically, you should just be able to implement the neural network in Spark, which would then be executed over several servers, and then
Uh,
that would be a lot more
I
efficient.
don't think that's allowed for the competition. I think we have to run everything on the car.
Okay.
We're not allowed to use like the internet to process anything.
Okay. Well then,
Yeah.
that would
That would be great if it worked, but yeah, they kind of shot us in the foot with all of this. I don't know why they did it, but
I
yeah.
mean, technically, the servers don't have to be in the cloud. Generally, they are, but you could have like just a bunch of you could have just several servers in the vehicle. I don't know if that also violates another rule. But no, but you can have just regular CPUs, right? Like
Yeah, we could.
because
As long as we
like
don't
the
use
servers
GPUs,
could
yeah.
be in the cloud, right? Like traditionally they are because you don't have to worry about lugging the servers around. But you can also just have a series of servers that have Spark on them, and they could just be in the car. And as long as they have Spark installed, then you can use the Spark language, and you could distribute them over several CPUs in a parallel fashion.
Very true, yeah. Definitely maybe something we should look into.
I don't know if anyone else has any. I only have like a little bit of like experience with Spark, but so I don't know if someone else has more experience in Spark and can maybe speak to more of the specifics, but it might be something that's feasible.
Anita could answer this.
I guess we don't really have a method of measuring error with like inside the car with the actual data going, but from our current testing, it is pretty accurate. I would say accurate enough for what we need. Are you asking, so like what we run the model with? I mean, that's a visualization done by Arvis, so like that's part of ROS. But we run the models with OpenVINO, which is something provided by Intel.
Awesome. Does anybody else have any questions? Otherwise, give it a couple minutes more. Okay, cool. Well, yeah, thank you to the perception team for the great presentation, and thank you to everybody for coming. I hope it was informative or interesting at least. If you want to, if you have other questions after this meeting, you can feel free to, you know, email the Autonomous if you're not a member of Autonomous, or you can, post on Facebook. And of course, for those of you in Autonomous, we have a Discord that you can message us in. So thanks, guys.
Guys.
Bye.